So one of the interesting things about chemical kinetics is that it can tell you the exact route that a chemical reaction takes in getting from starting materials to product. This route that the chemical reaction takes is what's called the reaction mechanism. And in this video, we're going to talk about how we can use chemical kinetics to show how exactly a chemical reaction occurs. So one thing that we haven't talked about a whole lot is the fact that whenever you look at a balanced reaction, it doesn't really tell you about how the reaction proceeds. All it tells you is what you start with and what you finish with. All right. So we're going to use this as an example. We're going to say one of A reacts with one of B to eventually produce one of C. So there's a couple of different ways that we could postulate that this reaction occurs. And we're going to start off with the simplest possible mechanism. All right, and that's going to be if A were to directly collide with B, and that would make C. All right, so this is the simplest type of collision. It's simplest type of route, and it's the most obvious, but it's not necessarily the only way that this reaction could happen. Often the way chemical reactions occur is that you end up generating what's called an intermediate. All right, and an intermediate is a chemical substance that gets created in one step, but then gets immediately consumed in a following step. So this next proposed mechanism shows an example of an intermediate. So what if instead of A colliding directly with B, what if two A's collided with each other and temporarily formed a bond? All right, so we create this chemical species right here, and this is going to be an intermediate. And the reason that it's an intermediate is you can see here in step 2, it gets consumed when it collides with B, and that creates 1C and 1A. So a little bit of vocabulary here. What we typically refer to as a chemical reaction is, we'll call that the overall balanced reaction. But all of these individual steps are what we'll call elementary reactions. All right. So again, whenever you have a chemical that is produced in one of the elementary reactions, but it's consumed in another one of the elementary reactions, we call that an intermediate. And hopefully you're familiar with this. Whenever you have a series of chemical reactions, if you ever see the same thing on one side of the reaction as you do on the other side of the reaction, they end up canceling out. So if we take these two elementary steps right here, you can see that this would cancel with this. So the intermediate, which is formed, immediately gets consumed. So it's neither an original reactant, nor is it a final product. Also, we consume an A in the first step, but we also generate an A in the second step, so we can cancel out one of those. So if we add up the reactants of both of these and the products of both of these, we end up getting the same overall reaction as we did in the first step. So this would be another possible mechanism to give us this overall balanced reaction. So each elementary reaction has its own rate law. And one thing that's different about an elementary reaction versus an overall reaction is back in when we were talking about kinetics, we said that to determine a rate law, we couldn't do it by directly looking at the coefficients in the overall balanced reaction. But if you're talking about the rate law of an elementary reaction, all right, which is going to be one of the specific steps in the overall reaction, you can do that by simply looking at the coefficients. All right, and okay, so the number of reactants that participate in an elementary step is called its molecularity. All right, so if you have only one thing that's involved in that step, it would be considered unimolecular. If there's two, it's bimolecular. If it's 3 molecules, it would be termolecular, although those are fairly rare. Okay, and so here are some examples of each of those types of molecularities. Okay, so we mentioned that each of the elementary reactions would have its own rate law. So for example, If this was the actual mechanism that the overall reaction had, this specific step would have its own rate law, and this specific step right here would have its own rate. But one thing that's interesting is that the overall rate of the overall reaction is determined only by one of those two elementary reactions. All right. So why is it that the overall rate law is determined by only one of the elementary reactions? All right. So we're just going to use this little analogy. It's a classic analogy used to describe this. We're just going to say that there's two toll booths. Here we have a road and we have two toll booths. And what we're going to do is we're going to measure the overall rate that cars can get through this highway, but we're going to be measuring it at the end right here. And if, for what it's worth, when we're measuring the rate of a reaction, we're measuring the products at the end of the reaction. All right. So first scenario we're going to have is where the first toll booth that you come to is actually the slow toll booth, and the second toll booth is actually really fast. All right. So what would end up happening there? All right. So what would end up happening is you would get a backup of cars right here, and they would only let cars through at a certain rate. But since the second one is the faster toll booth, the cars would essentially be able to make it through there as fast as they could get there. All right. So when you measured the overall rate, what you would see is that the overall amount of cars that you see in this part of the highway right here is determined only by how fast they would make it through that first toll booth. All right. So that first step controls the rate of the thing at the very end. All right. So let's take a look at the second scenario. Let's say that the first toll booth was really fast. It would let cars go through really fast, and by comparison, the second one was slower. All right. Well, what would happen then is that you would end up getting a backup in front of the second toll booth. All right. So ask yourself, what would control the rate that cars are coming out right here? It's the rate of only that second step. All right. It doesn't matter if this step right here, if this toll booth right here is slower than this one right here, the rate that they get through that first one doesn't have any effect on what you would eventually see. So the name for this in a chemical reaction is called the rate limiting step or the rate determining step. I've heard both of those used interchangeably. And the reason they call it that is that's eventually what determines the overall rate. So the way that we're going to use kinetics to figure out the mechanism of the reaction is we're going to first of all measure an experimental rate law. All right, and remember the rate law can be determined by running a set of experiments where you change the initial concentrations and you measure the initial rate, and we can determine that rate law even without knowing what the mechanism is. All right. And the second thing that we're going to do is we're going to propose a series of mechanisms, and we're going to figure out, based on what those elementary steps are, what the rate law would be if that were the mechanism. And in the end, if that matches your experimentally determined rate law, that would be that would give evidence that that is the mechanism. All right. So it helps to see an example of that. All right. So what we're going to do, we're going to start with this overall reaction. A plus B yields C. All right. And this is the data that we have by running those series of experiments and measuring the rate laws. We can see here, again, like if A gets doubled at a constant B, we can see there's a quadrupling of the rate. That means it's second order with respect to A. And with B, you can see in the data here, if that gets doubled, we get a doubling. So that's first order there. So this is the experimentally determined rate law. All right. And we can do that without knowing what the mechanism is. All right. So what our job now is to do is to try to come up with some ideas for different ways the reaction could occur. So if you look at that overall reaction right here, the most obvious thing is to suggest one single elementary step. All right, that would be if 1A collides directly with 1B to make 1C. All right. Well, if this is the elementary step, remember one thing that we said is that with elementary steps, you can determine the rate law directly by looking at its coefficients. All right. So if this is an elementary step, then its rate law would be this right here. All right, and the way that we get that is just by taking the coefficients and putting those in front of the after the concentrations. All right, and what this tells us is that this cannot possibly be the mechanism that this reaction has. And the reason for that is that if this is the actual mechanism, the rate law that we can get by looking at the elementary reactions would be the exact same as the one that we experimentally determined. And we can see that these are different, so therefore that can't be the mechanism. So let's suggest something else. Again, we're going to break this down into the two elementary steps where we have that intermediate. And whenever you have two elementary steps, inevitably one step is going to be slower than the other. All right, so in the first case, we're going to assume that the first step is the slow step, and that as soon as that intermediate gets formed, it's immediately going to, or it's relatively quickly going to combine with a B and make A and C. All right, again, it would create, overall, it would have the same balanced reaction. So if this were to be true, remember, the overall rate is determined by the slowest of the steps, just like in the toll booth example. All right, so what would the rate law for this elementary step be? It would be this right here. And again, we can tell that this is not the mechanism that this reaction is occurring, because this would be the rate that you would have. This would be the rate law if that were to be the case, and we can see that that is not the same as what we experimentally determined. All right, so the last thing is we're going to have the same two steps, but we're just going to switch the slow and the fast. All right, so if that were going to be the rate law would be the following. All right, and I'm going to go ahead and admit that this is probably one of the more complicated examples of this, but follow along and it will make sense. All right, so so the problem with this particular rate law is that this this right here is an intermediate. All right, so we don't have any way to have that as our experimental rate law, because there's no way when we're doing, we don't have a bottle of this intermediate laying around, so we can't control the initial concentration of that. But there's a way that we can deal with this. By the way, ignore these graphics right here. So so whenever this happens, whenever you generate an intermediate, and that is the faster step, what we have to assume is that the first step is a reversible reaction. All right. So if we assume that that first step is a reversible reaction, then we're actually going to have two rate constants. We have the forward one and we have a reverse one. And so if it's at equilibrium, and we're going to talk about equilibrium a little bit in the next unit, what ends up happening is that the forward rate equals the reverse rate. That's what happens when you have something at equilibrium. So these would be the two rate laws that we could have from those two steps, and we can set them equal to each other because the forward rate equals the reverse rate. And what we can do is we can solve for the concentration of this intermediate just by moving that rate constant over. And so these K1 and K minus 1, those are just the rate laws for the forward and the reverse, but they're both constants. And if you take a constant and you divide it by another constant, you get a constant. All right, so we can show that the concentration of this equals this expression right here. So plugging that back in and doing the math, we can see that eventually we get the exact same rate law as what we had before, and that proves that this is the mechanism.